Let's now consider this review problem, considering the reciprocals of integers that have a simple periodic decimal representation. First, let's prove that there are exactly two reciprocals of integers that have a period of exactly 1. To do this, we note that this happens if and only if the fraction can be written in the form n over 10 to the 1 minus 1, or n over 9. Now, for this to be written as 1 over something, that means that n has to be a factor of 9. So the factors of 9 are going to be 1, 3, and 9. So those are the possibilities. Now, clearly, 1 is out. That can't happen. But 3 and 9 do work. So if I have 1 over 9, that is equal to 0.1 bar. And 1 over 3 is equal to 3/9, and that's equal to 0.3 bar. And so that's a proof that 1/9 and 1/3 are the only two reciprocals that have a single periodic decimal representation when the period is exactly equal to 1. So the numbers are 3 and 9. Next, let's take a look at the problem of a period of exactly 2, and to show that there's exactly 3 of those. Well then, similarly, this must be a fraction of the form n over 10 to the second minus 1, which is n over 99. So if this is going to be 1 over something, then the something must be a factor of 99. Well, let's see. So 99 is equal to 3 squared times 11. And so there are 6 factors of 99, positive factors of 99, and the positive factors have the form 3 to the I times 11 to the j, where I is 0, 1, or 2, and j is either 0 or 1. So listing these out, we have 1, 3, 9, when j is equal to 0. And if j equals 1, we would have 11, 33, and 99. Okay, now 1 over 1 clearly is not going to work. 1 over 3 and 1 over 9 we have already discussed. And so the three possibilities that are left are 1 over 11, 1 over 33, and 1 over 99. And those indeed work as expected. 1 over 11 is 9 over 99, which is 0.09 bar. 1 over 33 is the same thing as 3 over 99, and that is equal to 0.03 bar. And finally, 1 over 99 is already in the appropriate form, and so that can be written as 0.01 bar. And so those are our answers. The three numbers are 11, 33, and 99. Next, we'll take a look at the numbers that have a period of length 3. So these must have the form n over 10 to the third minus 1, which is n over 999. And any number in this form has a simple periodic decimal representation where the period is a factor of 3. So 999, that's equal to 3 to the third times 37. That's the prime factorization. And so there are going to be 8 factors of 999, and they all have the form 3 to the I times 37 to the j, where I is equal to 0, 1, 2, or 3, and j is either equal to 0 or 1. So listing them out, we get 1, 3, 9, 27. That's if j is equal to 0, and if j equals 1, we get 37 times 3 is 111, times 3 is 333, and times 3 is 999. So those are the possibilities. Now clearly 1 does not work, and also 3 and 9 do have simple periodic decimal representations, but the minimal period is equal to 1 and not 3, so that's not going to work. But the others do work: 27, 37, 111, 333, and 999. So those are the 5 numbers: 27, 37, 111, 333, and 999. And let me do a couple of these real quick. So 1 over 27 is equal to 37 over 999. And so by our theorem, that is equal to 0.037 bar. 1 over 37 is equal to 27 over 999. And that's equal to 0.027 bar. And I'll leave it for you to check the other 3 to write them in something over 999 and to confirm that you get the decimal representation that you expect. Lastly, we have period 4. So this will have the form n over 10 to the 4th minus 1, which is n over 9,999. And so by the same pattern, if it's 1 over something, then the something must be a factor of 9,999. Well, the factors of 9,999, well, this factors as 3 squared times 11, 99, times 101. And so the factors will have the form 3 to the I times 11 to the j times 101 to the k, where I is 0, 1, or 2, j is 0 or 1, and k is 0 or 1. So listing out the possibilities, we get 1, 3, 9 if both j and k are equal to 0. If j equals 1 and k equals 0, then we would get 11, 33, and 99. If k is equal to 1 and j equals 0 and 1 through the values of I, we would get 101, 303, and 909. And finally, if j and k are both equal to 1, we would get 1,111, 3,333, and 9,999. Okay, now not all of these will have a period of 4 minimally. 1 clearly does not work. We know that 3 and 9 both have 1/3 and 1/9 have a representation with period of 1. We've also established that 11, 33, and 99 have a representation with period 2. So period 1 and period 2, 1 and 2 are both factors of 4, but the minimum length would not be equal to 4. So here are the 6 that have a representation of decimal representation of digits of exactly 4. 101, 333, 909, 1,111, 3,333, and 9,999. So those are the possibilities. And just to do one of them to confirm this, we would have that, for example, 1 over, let's do 999. So 1 over 999, for example, sorry, 1 over 909, pardon me. That is equal to 11 over 9,999. And so the decimal representation would be 0.0011 bar. And the others can be treated as similarly.